Hello, everybody. This is lesson 10.3, kind of the beginning of the second half of chapter 10. So we've already done intervals and tests with proportions, and here we go. We have intervals and tests with means. Um, we're going to do an interval with cookies and then a test with basketball. Um, so let's just dive in. Um, if I were in school today, I would be bringing you cookies right now. Name brand Chips Ahoy cookies, and then the generic brand is called Benton's, and this is what they look like. I mean, you can see Benton's is really trying to rip them off, like, we look the same. Um, but interestingly, if you care, these Benton's cookies are about half the price of Chips Ahoy cookies. So, whatever that's worth. So, if we were in class, I'd give you each a cookie from each bag. You would do your best to count the number of chocolate chips in each cookie as best you could. Okay. So, what I have here is this is all the data from last year when I did this. Um, Kids took the cookies, counted as best they could, looking at both sides, how many chocolate chips were in each cookie. The Chips Ahoy, here's the data. On average, it was 15.2 chocolate chips. The generic brand was 14.7. Here's their standard deviations, and both of them had a sample size of 17. So this must have been a small class, or maybe there was a field trip or something that day, but only 17 kids did this. So there were 17 of each cookie. We're going to make a 95% CI, confidence interval, for the difference in the means of each cookie. We're going to go Chips Ahoy minus Benton's. The difference in the means is 0.5, and we're going to make the interval. So that 0.5 is going to be the point estimate, which means it will be the middle or the center of the interval. Okay. To be specific, what are we measuring? What is our parameter? It is mu C minus mu B. It is the true difference in mean number of chocolate chips in the cookies. And then I'll even say Chips Ahoy minus Benton's. Benton's is the generic. If you go to Aldi, you'll see Benton's. The name of the procedure is a two sample, because we have two kinds of cookies. It is a T interval because, remember, it's a T because we are doing means. And then you can even say what for. It is trying to measure mu C minus mu B, the difference. We're going to kind of take the easy way out here with the conditions. When you have processes like these for both cookies, they're just mass produced in a factory. And those processes are in mass quantities, they're streamlined, so we can assume that the population distribution of all the cookies that these guys make, you can pretty much assume it's going to be approximately normal, and that the samples are going to be random because they're just random bags produced from these factory processes, and that the number of chips in each cookie is independent. Because there's no way we're approaching, with 17 cookies, there's no way we're approaching 10% of all the cookies ever. So we're good on the conditions. Here is the formula. This is on your cheat sheet. The center is with x bars. At the beginning of the chapter, it was P1 minus P2, P hat 1 minus P hat 2. Now it's x bars. We already did that. That's these numbers right here. So that is 15.2 minus 14.7. Okay. We already know that's 0.5. Okay. Then you've got your plus or minus. We have to go searching. What is T star going to be? Well, to get T star, you may remember you have to know dF, degrees of freedom, take your sample size minus 1, which is 16, and then we got to look that up, the T-star up, the critical value in your College Board packet. So let's go there. Oh, by the way, if you're wondering, here's page 2 right here, and we are doing means, right? And so voila, look at this. This is what you're about to see in the formula. That is the standard error of the two samples. And we just did this too, didn't we? X bar 1 minus X bar 2. So this is where you're looking for means, but that's not where we're at. We're going down to the table with the degrees of freedom right here, table B, and I need 16 degrees of freedom. And then where does that cross with 95%? So I've got 2.12. That is the critical value, 2.12. Okay. Then there's that square root thing that I just showed you in the packet, right? I'll write it all down, but then I'm going to really have the calculator help me. This is the standard deviation of each type of cookie. So 4.7 squared over 17 plus 3.9 over 17, oh, squared. Okay, this is the standard error. If I put an orange box here, the orange box is the margin of error, MOE. So I like drawing my interval like a line, like I always do. I already know the middle of my interval is going to be 0.5, half of a chip, and now I'll just ask the calculator to get me the two endpoints. You could try to do this by hand if you want. This number is what you add to 0.5, and it's what you subtract from 0.5. I have, let's see, I think I saved it. Yeah, lesson 10.3. So I put in a t-test with all the numbers. If you want to see how I did that, it's where it always is. Put your stats in here, and then you do the second sample below it. I put Chips Ahoy first, and then I put Benton's second, and just put it in carefully. Okay, so I'm not going to do it twice, but I have it here, and then I just do the drop down on the interval right there. Make sure it's 95. It should be the default. There's my interval. So the low end point is negative 2.5. I'm just going to chop off the decimals to speed up a little bit to 3.5. So it looks to me like the margin of error from here to here is plus 3, and then from here to here is minus 3. That's my margin of error. MOE is 3. So if I were to crank out this on the calculator, I would get 3, roughly. Probably some decimals in there. If you do the 3 dots over here on Desmos, voila. See the 1.48? That would be the square root. This is 1.48. Okay, for what that's worth. On the TI-84, stat tests, where is it? The two sample T interval, C button 0, 0 right there. And take your time, put everything in carefully. Chips Ahoy first. See, I'm not being careful. 17 is the sample size for both. And there you go, same interval. Okay. You might notice there, I'm just looking at the calculator, degrees of freedom, it says it's 32. Um, for now, don't worry about that, okay? I'll explain it in a later lesson. In this situation, there's more than one accepted way to calculate degrees of freedom. But for now, we can just stick with this, okay? Trust me. All right. So I've got my interval. Now I just need to interpret it. We are 95% confident that the true, let's see, this difference, is this cheating? Whatever, I'm cheating, is between negative 2.5 and 3.5 chocolate chips. Okay, there it is. Based on the interval, is there convincing evidence that Chips Ahoy has more chocolate chips per cookie on average? Is this convincing you? Basically, we've done this many times. 0, 0, 0. Is 0 in this interval? Sure it is. It's right about there. That would be roughly where it is. But if it's in there, that means 0 is a possible difference. 0 represents when the cookies are the same. So is it convincing? No, since 0 is contained in the interval, it is plausible or possible that the two means are equal. So if the entire interval was, say, positive, then this would be yes. But it doesn't. The interval straddles 0. It has positive numbers and negative numbers. All right, so there's our first interval. Okay, now to do a test, we're going to revisit basketball. Um, Michigan versus Michigan State. As I'm writing this, I think Michigan is playing tonight in the NCAA tournament. I think they're both playing, actually. They're on opposite sides of the bracket, but they're both still alive. They could win and go to the Elite Eight. We're going to compare here the number of points that these teams score per game. 30 games for Michigan, 33 games for MSU, Michigan State. You have their average points per game. You can see Michigan is a little bit higher in points per game. Is it, we're going to run a test. We're not going to do an interval. We're going to do a test. Do these data provide convincing evidence? Whenever you see that, it typically means, hey, do a test. Is there evidence of a difference in the mean number of points scored for the two teams at the 5% significance level? So that means my alpha is 5. So X1, I'm calling that Michigan, and X2 is Michigan State. And the difference between these two is 2.3 points. So in this sample, the difference is 2.3 points per game. Do you think that's going to be significant? Is that going to be convincing that Michigan scores more points than Michigan State? Well, let's figure it out. So the parameter is going to be mu1 minus mu2 because I defined my mu's, right? I wrote them down here, which you can do as well. Um, it is the true difference in points, in mean points per game. I don't even need to say Michigan minus Michigan State, right? Because I already defined mu1 here and mu2 there, so I've got it. My statistic is the 2.3. It is the x bar 1 minus x bar 2, which I already calculated up there. Okay, my hypotheses, we did this before break, it's been a while. Remember, the null is always that the two schools are the same. So you could say mu1 equals mu2, or you could say mu1 minus mu2 is 0. HA is that you put a less than here, a greater than here, or maybe a not equal to. Well, you let this word guide you right here. It said, is there a difference? It didn't say, does Michigan score more? So I'm just going to say a difference. Or you could write mu1 minus mu2 doesn't equal 0. Um, the evidence for my HA, like why I did that, I guess the evidence is that 70, well, the samples are not equal, right? These are not equal. That's what I'm saying right there. All right, the plan, the name, it's a two-sample t-test. Two schools, two samples, and it is a t-test. We're not doing an interval because it said, is there evidence? Okay. Conditions, was it random? I think it stated that. Let me go look for that. Did it state random? Random here, random here. We're good. CLT is met because 30 is greater than or equal to 30, and 33 is greater than or equal to 30. Therefore, we have enough sample size to say that these data distributions will be approximately normal. Woohoo! Um, are the games independent? I did a little pre-work here. We've got 30 games here, 33 games here. I multiplied them by 10 to get 300 and 330. Has Michigan played more than 300 games? I put ever. Um, I guess if we're talking all time, then yeah, this is fine. I've taught this lesson a couple times, and kids say, well, wait a minute, it's a different team next year, and it was a different team last year. You could argue that, but I think we're going to try to say more globally, Michigan all time, or at least, maybe the last 10 years, they've played more than 300 games in the last 10 years, probably. I think they play 35 games a year, maybe 40 games a year. Depends on how far they go in the tournament, I guess. But so you can maybe put a question mark by this, but at least I've addressed it. Okay. Um, let's do the work. Remember, the middle of the curve is 0, and I'm going to try to figure out where my sample is. My sample is right here at 2.3. So I'll just draw an arbitrary line here and say, okay, 2.3. And I'm trying to find this shaded area to the right. I'm also going to shade over here at negative 2.3 because remember, this is a two-sided test when I do a difference test, okay? So I have both tails to consider. All right, to get my test statistic, here is the formula that I do to get my test statistic. So x bar 1 minus x bar 2, that's my numerator. I already did that. It's right here. It's 2.3, okay? Easy peasy. Because that's essentially saying how far is this from 0? I mean, you may remember when we did proportions, I put minus 0 here, but you never need to do that, right, folks? So forget it. Let's just do 2.3. And then the denominator, again, that was there for the interval at the beginning. This is the standard error, the combined standard error of Michigan and Michigan State, which was, I need their standard deviations. Michigan's was 11.1 and 5.2 for Michigan State. So square root of all of that. 11.1, 5.2. Michigan only had 30 games played. Michigan State had 33 games played. Add them up. What we're really doing, if you remember, when you combine standard deviations, you actually add variances. Because remember, when you square standard deviation, you get variance. So voila, it's all working. Let's do this actually by hand, and then I'll have. Oh, come on, go. Why don't you want to split screen? Weird. Don't know why you won't. Let's try it. Hmm. Oh, there. Whatever I did, I don't know why. So to do it by hand, it's just 2.3 divided by the square root of 11.1 squared divided by 30 plus, oops, not there, there, 5.2 square, oh, fag, plus 5.2 divided by 33. Voila, look at that. So that is going to be my test statistic, 1.03. Yikes. Okay, so there you have it. And to get the p-value, I'm going to let the calculator do it for me. Inference, t-test, stats, put in Michigan first. Sample size was 30 games. They scored 77.9. Standard deviation 11.1. Add Michigan State's in. They played 3 more games. Their standard deviation. They're much more consistent, or less spread out, I should say. Create the test, do the test button, and there you have it. Look, it's already, see, I want both highlighted because it's two-tailed. And the test statistic is 1.036. Hey, look, it matches. I got it right. Just doing it by hand. And the p-value is 0.306. If I hit the right tail only, this is somewhat helpful. I now know that this tail is 0.153. If I do the left tail, oh, I can't do that, but it shades too much. This is also 0.153. That's what it means to be two-tailed. Okay? Um, Piece of cake. What is our conclusion? With a p, our p-value is 30%. We compare that to our significance level of 5%. It is way above it. Remember, if the p-value is low, reject HO. This p-value ain't low. We will fail to reject HO. And when you do this, remember, you say, there is not convincing evidence of anything going on here. Okay? There is not evidence that Michigan scores more points. Or, sorry, I'm not saying it right. That Michigan and Michigan State, I'm not saying this well. This is always the part I have to slow down on and think. That the mean points per game for Michigan and Michigan State, woo, are different. Because remember, we're not testing if Michigan's was greater than Michigan State's, right? I'm pulling this from way back up here, or also from here, that they're not the same. So that is how you would conclude that. Um, so again, we did most of this on the calculator, but state plan do conclude, and then your HO and HA look like this for the homework because we have mu's, we're doing averages. So there you go, folks. Enjoy that lesson app. It's going to be awesome.